This workshop, I make a general introduction. I will make an additional short presentation about the process from the European call to the demonstration. And then we have a first session devoted to the scientific characterization of the music prototype. So the music prototype is the ComBioTES prototype. Then we have a second session presented by people from DTU about the real-world characterization of the same prototype. So you will have the two aspects of this music prototype in perfectly controlled condition and in real condition. Then we have a session 3 with people from the work package 6, I mean the techno-economic and the elements. So they will present some elements obtained during the project and some tool developed during the project. And something important during this, at the end of this session also will be some feedback at the end of the project and some feedback about some issue that we faced and that can be perhaps avoided for the further project. So is there any question, any comments before we really enter the workshop? Okay, if not, I will continue with a very non-scientific presentation. Just what is called from design to demonstration. And as I said just before, the goals expected by the call are this one. In green, you can see the goal that we choose to address. So we choose to address building, heating, and cooling system, energy storage, intraday. So that means interseasonal storage has been rejected. We choose to address also new materials for PCM storage. We choose to increase the competitiveness of renewable technology through thermal storage, and the use of thermal storage. I remind just the detailed concepts. So basically, I just give a few words about it. And so it was the first shimps, the very first concept that we developed for both storages. So basically, for the music prototype, we choose to consider tube and shell configuration with water flowing in the tube and PCM inside the shell. We choose to use thin tubes, vertical configuration, and we choose to address domestic hot water and space heating. For the versatile TS, it was more open, more free. And we choose to try to develop something a little bit new. And so the main configuration, it is a water storage in which we have added a heat exchanger. And the main concept is that for the heating, this is a water thermocline. And for the cooling, this is a water ice PCM storage with direct contact between the water and the ice during the discharge. So then after the first concept, we need to go on with the design. And so we use basically the same kind of approach for both prototypes. So that means that we selected at the beginning some possible combination between the tubes. We insert the size of the tubes, the configuration, so the size of the fins, the density of the fins, and so we have this kind of screening. At the and this step. As a conclusion, we have some first element in some first pairs of tubes, inserts, heat exchanger size. So we continue with purely static calculation, purely energetic calculation, just to have a very perfect evaluation of the energy expected. So it is based just on basic energy calculation. And so at the end of this second step, we have a kind of very generic design. Then we performed some dynamic simulation using the dynamic model. It was coded in Daimola. And the objective is to assess the operation and to assess the gap between the perfect design and the real dynamic design. So, and then we have to continue, for example, for the music prototype, due to the condition, we have to see if in which kind of regime we are, if it is laminar, turbulent, if we are in convective flow, if we are in forced convective flow, in natural convective flow, in mixed convective flow. Then we perform a lot of parametric study and sensitivity study to obtain what we can call a kind of final paper design. So that means only based on calculation without it. And basically to do that, this is just illustration. So we consider a lot of different configuration of tube bundle. For example, we considered a lot of different tube configuration. The effect of pins, the effect of the size, and so at the end of this process, we obtain, as I said, the final paper design. That means that this is a purely theoretical design. In parallel, we perform some studies on the PCM material. Both for the PCM storage and for the versatile storage. For the PCM storage, we try to characterize or recharacterize a promising PCM, which is called the isosobide. And so we perform tests from very, very small scale, measuring at DSC scale the material performances. Then we perform some measurement at intermediate scale and prototype scale to see all the performances at all scale. And for the versatile TES, we try to develop internally a kind of macro encapsulation of PCM to increase the storage capacity of the versatile TES. This step were made in parallel with the design of the storage. And at the end of both of these elements, we have this very paper design. So basically, we have the configuration of the tube and shell with some dimension. We have the configuration of the tube bundle, so the size of the tube. In red, you can see that also we have decided to consider internal heating, which was quite new, which is quite new in this kind of storage. The objective was mainly to obtain a fully autonomous storage. And for the music prototype, we also consider a new configuration for the fluid flow. So that means that the water is not flowing from the top to the bottom or from the bottom to the top, but we are considering a 3 passes fluid flow. So that means that, for example, in charge, the fluid is passing from the top to the bottom on this tube bundle, but not the entire tube bundle. Then the water is going from the bottom to the fluid flow on the second pass and the final pass from the top to the bottom. Calculations show that it may increase significantly the performances. So we try it. And we have also the paper design of the versatile TES with the macro encapsulated PCM and the serpentines inside the water with the different dimension. The next step has been the mechanical engineering. So that means we have to consider for both storages all the constraints from mechanical aspect, the configuration, to take into account the pressure, into account the temperature, the manufacturing constraint on process, to consider and to define the fluid inlets and outlet system, the fluid distribution system, the embedded instrumentation and the way to put this embedded instrumentation inside the storage. All the regulation and the norms elements, all elements for the supporting, the lifting, the anchorage, the insulation, the safety content. It has been partially subtracted because this is not our job. And we finally obtained the technical drawing okay for manufacturing. Then this is the manufacturing. So you can see a different step of the manufacturing of the music prototype. And different step of the manufacturing of the versatile prototype. We have also put a lot of instrumentation and mainly thermocouples inside all these prototypes. And it was really not an issue, but a big job because, and mostly for the music prototype, to install the thermocouple, that means that it implies that all the steps of the manufacturing and the instrumentation are synchronized. So that means that some thermocouple has to be installed at given step, then the manufacturing is going to the next step, and then we have to install new thermocouples. So it has to be, it creates a lot of interfaces between the CA with installing the thermocouples and the manufacturer. It was a little bit easier for the versatile because it can be installed only during the manufacturing of the serpentine heat exchanger. And finally, after all this step and all this, a lot of problem, a lot of issue, we have the different prototype. I mainly focus just for illustration at the prototype that are tested at CA. So you can see the final prototype of music. And so finally music is a TES tank, and we chose during the project to develop and to provide to the demo site a skid and fully autonomous skid to try to reduce all the modification of the demo site. And you can see also the versatile TES installed on the test loop to be tested. You can see here just the test loop developed during the project to test the versatile, because we need a main circuit in water and a secondary circuit in glycol water. You can see also for the demonstration site the prototype of music at DTU, the prototype of music at INES, and the prototype of the versatile at EECS in Beijing. And so, if you have some questions, some remarks, some anything about these two first presentation.
So when you have this design with the PCM where you have water free flow, so you don't have forced flow water.
Yeah. We have forced flow.
Okay, so it's a turbulent regime you're in.
We have to check two different points. We have to check if it is laminar or turbulent, okay. Just to be sure that we have enough heat transfer coefficient inside the tube. And we have to consider also that we are not in mixed convective flow, because it is even for all PCM storage and in this configuration, if you have mixed convection, that means that you don't really know what happens. And in our configuration, since we have water flowing from the top to the bottom and from the bottom to the top, that means if it is mixed convective flow, we have no idea what happens. So we have to check that every configuration considered is really in forced convective flow.
Yeah, yeah, because it matters very much with the heat transfer and
yeah.
How about, if I may ask one more question?
Yeah.
So you test the PCM material, new material, different sizes.
Yeah.
Is there a different reaction when it's a very small particle with a lot of surface compared to when you have bulk and you have thermal transmission through the...
Yeah, exactly. And isosorbide, the one we tested, has been tested because it is one of the product that is manufactured by one of the partners, and it has a very high latent fusion enthalpy. So it was quite okay on the paper, but it has overcooling. So we perform, we wanted to see what happens. And when you perform some measurement at DSC scales, so it is few micrograms, the overcooling is absolutely enormous. So that means that it is supposed to melt at 55, 60 Celsius degrees, but the solidification occurs at 5 Celsius degrees. If you put it in bigger scale, the overcooling will be reduced from something like 50 Celsius degrees to 20 degrees, but you still have overcooling. And so it was not shown, but we try also some measure to reduce overcooling, and namely it was bubbling. So you have some air or nitrogen bubbling that creates some shear stress, and this shear stress is expected to initiate the solidification. It works.
So it's kind of a seed effect.
Yes, but in fact, you reduce the overcooling, but you still have overcooling, and you can reduce. We succeed in reducing maybe to minimum something like 5 degrees, 6 degrees, but we still have overcooling, and it is still a stochastic phenomenon. Sometimes you are performing 5 times the same test, and you have 2 or 3 different patterns, and you don't know which one will appear.
Oh, okay. Thanks.
So if there's no additional question, maybe we can continue with the scientific characterization of the music prototype.
Morning, everybody. I'm Bénédicte Champel from CEA, and I will present you some results of the scientific characterization of the music prototype that was carried out at CEA during the project. So I will shortly remind how the music design looks like, and describe the instrumentation that has been put in the prototype at CEA. And I will finish with the analysis of the steps performed and a short synthesis, and we could do next to continue on the subject. So this has already been presented by the project coordinator. The storage concept for music is a tube and shell latent heat thermal energy storage. For the design, 2 use cases were considered. One use case for the supply of domestic water for a 5-person household, and the other use case considered was a space heating use case adapted from constraints on DTU demonstration site. So the tank design, again, this was presented by the project coordinator with the geometry, the tube bundle, and how it looks like. And there were 2 innovative features in the design compared to state-of-the-art tube and shell thermal energy storages. The first one is that the hydraulic pattern was built in split paths, which is not very usually encountered for vertical tubes. It's easier with horizontal ones. And the second innovative feature is that we decided to install 7 electrical cartridges, so internal heaters, inside 7 of the 37 tubes of the storage. So the tubes equipped with internal heaters are represented in red in the sketch here. So they are distributed in the storage. So the final tank design looks how is represented to the left of the pictures. So there are some modification to the initial design done during the engineering phase. The top plenum has a different geometry. It's represented here. In the initial design, we had noticed that the smaller the distance between tubes is, the better it is for energy recovery during discharge. And we wanted to have a fin pitch, so the distance between two fins, the fins of two adjacent tubes of 1 millimeter. But due to manufacturing constraints, it was not feasible. So the fin pitch was increased to 2.5 millimeter. And also we had a larger shell diameter because of standard dimensions of shells. And as a conclusion, the quantity of PCM in the storage is higher in the demonstration than what was planned initially. So I talked about the tank, and now I talk about the system. So here is the tank. And the tank is part of a system with many other components that are presented here. And if I just explain how it looks like, so there are sensors and there are also additional components. There are components here presented in green. It's a hydraulical loop for the external charge. As the internal charge was quite innovative and we were not sure if it would function properly, we decided to add a backup and to have an external charge with an external loop, hydraulical loop, with a pump and with a specific heater to be able to charge the storage efficiently if the internal charge was not functioning properly. We also added to the loop a mixing valve to ensure to have a constant output temperature, constant outlet temperature. Sorry, because the characteristics of latent heat thermal energy storage is that during discharge, the temperature at the outlet of the storage decreases. It's high at the first stages of discharge, and then it decreases, and eventually it reaches a low temperature. You still are able to extract energy from the storage, but the temperature at which you recover the energy is quite low. In the use cases we had, we needed a constant temperature at the outlet of the storage. So we decided to install a bypass of the storage and to have a mixing valve. And so the flow rate in the storage and the flow rate in the bypass are adjusted due to this mixing valve to ensure to have a constant mixing temperature at the outlet. So I'm just teasing, it does not really work, but you will see it later. And in purple to the right, you see the connection to the demonstration site. The performance of the design. So I calculated the energy stored in the prototype between 30 and 75 degrees, and the energy corresponds to 18 kilowatt hour. 10 kilowatt hour from the latent heat of the PCM. You can see that the sensible heat of the PCM is quite large, 3.5 kilowatt hour. The sensible energy of the water in the plenums and in the tubes is also quite large. And there is also sensible energy of all the metallic components, the tubes, the inserts, the fins, the plates, the shell, and so on. So 18 kilowatt hour, of which a little bit more than half is latent heat of the PCM. So this is for the between 30 and 75 degrees. And Anish from DTU will later present you results of tests done at DTU. And here the two temperature, the range of temperature was between 60 and 80 degrees. And between 60 and 80 degrees, the energy stored in the prototype is 13.7 kilowatt hour. But it's the energy when you consider that everything is at 60 degrees at start of charge, and everything is at 80 degrees at the end of charge. And also the shell and the plates and so on.
Can you ask questions?
Yes.
Okay, so the sensible part, is that all the stainless steel and so on?
The dark one, yes, the gray one, it's
brown one.
yes, this is stainless steel.
How about the sensible PCM that is 3.6? So
Yes, because PCM also has a specific heat.
Oh, okay.
So when you the PCM melts at I didn't say that the PCM melts at 70 degrees, but
so if you calculate just around the 70, the melting point, then all the others will be smaller, right?
Yes. Yes. Just the latent, it's 10 kilowatt-hour.
Yeah.
And you see that if you increase the temperature range, you can have a quite huge amount of energy in sensible.
Yes.
So here you already saw this kind of pictures. Regarding the instrumentation, so at CEA Grenoble, the instrumentation was quite important because we wanted to be able to characterize in details the behavior of the system. So here I talk about the tank instrumentation. So there are almost 100 sensors in the tank. Temperature sensors, pressure, flow rate, and level sensors. Most of them are for scientific purposes. Some sensors have been installed for the assessment of the state of charge of the system. So there are two possibilities of assessing the state of charge of the system from the sensors. There is one possibility with temperature measurement at different locations in the tank, and we also added vibrating blades to be able to follow the modification of the level of PCM, because when PCM melts, its density decreases, so the volume it occupies is higher. So the level gets up when it melts. Okay, I don't go into more details. And so what test did we perform on music prototype? At first, we performed tests with hydraulical charge and discharge because we wanted to be able to assess the performance with clean conditions. So this is not the operation that is planned in real operation, but we wanted to be able to monitor everything with clean conditions. And then we perform tests aiming at assess the performance with conditions representative of applications. So with external charge, with internal charge, and with what we call ComBioTES discharge. So using the mixing valve. Okay, so I will go into this. I will follow this. I will follow this to present the results. So I start with the hydraulical charge. So we did different tests with nominal conditions. So our nominal conditions were between 30 and 75 degrees. And we did tests modifying the flow rate of the heat transfer fluid. So the nominal conditions we were at, there are no units, 1,200 kilograms per hour. So that's 20 liters per minute. And we did tests. We repeated the test to check if it was repeatable, and we modified also the flow rate. We modified the initial temperature to see what is the sensitivity of the performance to these parameters. Here I show you for a test that has lasted 3 hours, the evolution of the outlet temperature of of the tank during a charge. So the initial temperature of the storage was 30 degrees, and at one test it was 20 degrees, and we charge the storage with a heat transfer fluid with a temperature of 75 degrees. And here you see that the heat transfer fluid outlet temperature, of course, increases with time, and this increase depends on the flow rate. But this is quite normal, and you can see that it is quite repeatable. Looking at the power that is given that is transferred to the storage, the curve is quite usual. At first, in the first instance, there is always a peak of power, and then the power decreases. And you see that the maximum power that is obtained is correlated with the flow rate of the heat transfer fluid. Here is the energy that is transferred to the storage as a function of time for the different flow rates of the heat transfer fluid. You can see that for 600 kg/h and 1,200 kg/h, the curves are quite similar. The curve is mainly different for 300 kg/h because here the transfer is limited also by the heat exchange between the fluid and the tube. And here is the same figure as previously, but I pushed the time to 6 hours just to show that we did not observe a stabilization of energy transferred to the storage. So the energy that we should reach is 18 kWh. For one test, we went over this energy, which means that we have heat losses. And in any case, we never observed stabilization of energy. So we have to do more tests to understand what is going on. We think that maybe the localization of the flow meter is not correct. So we have to work on that.
The brown line seems to stabilize.
That's this one.
Yeah.
That's yes, a little bit more. You're right. Here is a figure showing the evolution of PCM temperature around the tubes. So I plot 15 PCM temperatures and 5 in each pass. So as was presented, the hydraulical part of the tank, we have 3 passes, and the temperatures around the central pass are presented in yellow. Around the intermediate pass, they are presented in blue, and around the outside pass, they are presented in green. And you can see that. Sorry. And you can see that the evolution of PCM temperature in the tank is consistent with the flow direction. We observe a clear temperature plateau at 70 degrees, which is the PCM melting temperature. At the end of the charge, we observe temperature oscillations. So when the PCM is liquid, that could be due to convective effects, because the PCM is liquid. We have to work on that. Also here, I present the evolution of the temperature of the heat transfer fluid in the plenums. there are four plenums. There are four hydraulical plenums in the system, and in the flow direction, the temperature encountered in the first plenum is shown in dark red. In the second plenum, it's shown in normal red. It's difficult to see the difference. In the third plenum, the temperatures are shown in orange, and the last plenum, the temperatures are shown in green. And you can see that the evolution of temperature of the heat transfer fluid is consistent with the flow direction. The temperature is homogeneous in the plenums for almost all plenums, for the top inside, bottom inside, and bottom outside plenum. But the temperature is not homogeneous in the top outside plenum. And I thought I had a view of the location of the thermocouples, because the two curves that are at the bottom are linked to thermocouples 134 and 138, and those thermocouples are at the edges of the plenum. So it means that the flow, there is no real mixing in the plenum. So this curve was obtained with a high flow rate, and if we decrease the flow rate, it's more homogeneous, but I don't show it here. And I think finally for the hydraulical charge, here is the temperatures of, we have some temperature sensors near the shell. So in blue and in gray, the temperature sensors are outside of the tube bundle, but near the tubes. And the orange one is outside of the tube bundle and at the furthest location from the tube bundle. So really near the shell, where there is a huge thickness of PCM. And if you look at the evolution of temperature of these at these locations during first 3 hours of charge, you can see that none of these thermocouples has reached the melting temperature of the PCM. So it means that it takes a long time to melt all the PCM. And this is what we expected, because the thermal conductivity of the PCM is really low. So it's when the PCM is within the fins, we have an effective thermal conductivity that is not so bad, and around 10 watt per meter per Kelvin. But when PCM is free, so there is only PCM, it's not conductive. The conductivity is below 1 watt per meter per Kelvin, so it takes a long time to melt it. So it means that charge is not finished after 3 hours. That was a change. So here were just the locations of the temperature sensors in the top and bottom plenum. And for the top outside plenum, the sensors 134 and 138, they are located here. So they are outside of the tube bundle. Just to show you. Here are the tests that were performed on music prototype with hydraulical discharge. So the temperatures are exactly the same, and we did some sensitivity to the flow rate of the heat transfer fluid with the nominal conditions at 720 kilogram per hour. So that's 12 liters per minute. It's a good shower. Here is the evolution of the outlet temperature with time, with a discharge that lasted 9 hours. So here you can see that at the end we reach stability, and we reach 30 degrees, and we observe that the decrease in outlet temperature depends on the flow rates of the heat transfer fluid. which is expected.
So one question.
Yes.
Not so much of this, but then is it symmetric or the heat transfer in PCM, is it the same when it's solid as it is when it's liquid? Because otherwise, then it would be symmetric, I guess, with charge discharge.
First, it's not totally symmetric because the heat exchange depends on the resistance. So on the flow rate and on the resistance on the other side, in the PCM, and it also depends on the temperature difference. And when you are in charge, the PCM melts at 70 degrees and you charge with 75 degrees heat transfer fluid. So you have only 5 degrees temperature difference. And in discharge, you have 30, you have more difference in temperature. So the power should
transfer all the heat conductivity.
Yes. The thermal conductivity of the PCM is different in solid and liquid, but as we do not consider just the PCM, but we consider the PCM in the field, the effective conductivity is almost the same. Here you can see the maximum power just before, and again the maximum power is correlated with the flow rate. The energy that was retrieved from the storage. So we observed that it's possible to stabilize the energy that is retrieved. With some tests, we are above the 18 kilowatt hour.
That's not
means that we are creating energy. It's perfect. So we have to understand what happened in this test. And for other tests, we are below. So we have to work on it. And there is no real repeatability because the blue, green, and yellow curves were supposed to be obtained under the same conditions. And actually, they were probably not obtained under the same condition. And this is probably due to the fact that actually, when we do charges and then we do discharges, we do cycles, and we probably never achieved a real isothermal temperature in the storage at the end of the charge. We never waited long enough to be sure to be exactly at 75 degrees as supposed. Well, remember when I presented you the temperature of the PCM near the shell? It takes really a long time to stabilize its temperature, and probably the 3 charges that were done before those 3 charges did not last the same duration, so we had not the same initial state of the storage. Again, here is a presentation of the temperature of the PCM in the passes. So the evolution of temperature is consistent with the flow direction. In discharge, we observe 2 temperature plateaus, one at 70 degrees and one at 65 degrees. Charge. ICEA on other storages with the same PCM. And one of our students in the lab did some DSCs of the PCM, which is RT70HC, and she did DSCs varying the temperature ramp. And when she had a very, very low temperature ramp, she also observed 2 peaks in DSC. So our understanding is that this PCM is probably a mixture of two elements that have different melting temperature, different phase change temperature. And it's observed in discharge and not in charge. I don't know why. Here again, the temperature in the plenums. It's a little bit more homogeneous than for the charge. This might be due to the fact that the flow rate is lower. It might also be due to the fact that in discharge and in charge, the flow direction is different. So this might change a little bit the things. But we still have something with one thermocouple that has a very, very, very low temperature. So I arrived to the external charge. So to remind you, for the external charge, we have one external loop, external hydraulic loop with a pump. And in this loop, there is a heater that has a heating power of 3 kilowatts. And this heater is controlled. There is a temperature sensor at the outlet of the heater. And if the temperature of the heat transfer fluid reaches a set point or a security temperature, the heater is stopped, but not the pump, but the heater is stopped. So we did some tests with different flow rates controlled by the pumps and with different temperature set point, 75 and 80 degrees. So here is the profile of power given to the transfer to the tank as a function of time for the 4 tests. You can see that the power transferred is on the order of 3 kilowatts, which is normal. It's the power of the heater. You can see that the max temperature reached is, so the heater stops at one point. And for the blue, orange, and yellow curves, we had a limit of 75 degrees, and for the green one, we had a limit of 80 degrees. And you see that if the limit is 80 degrees, the duration of the charge is larger, which seems reasonable. In some tests, at some point, the pump is stopped. It stops automatically. We don't know really why. Okay, so the power is almost constant with 3 kilowatts. We didn't here in this test see impact of the flow rate of the heat transfer fluid on the power or on the time, on the duration of the charge. And if I plot the energy that is transferred to the storage, you can see that the energy that is transferred to the storage as a function of time, so it's linear due to the fact that the power is constant. And with the high temperature, we transferred almost 17 kilowatt hour to the storage. And with the low temperature set point, we transferred 14 kilowatt hour with the high flow rate, and only 12 kilowatt hour with the low flow rate. Okay, I now arrive to the internal charge.
Yes. So the previous slide. Yes. So if you have this smaller transfer at the low flow rate, then you are discarding something because you're inputting the same power, right? So some of it is just going through and disappearing. Or why would you see the difference? I know you have different flow rates, but you're still providing the same power.
Actually, I did a mistake when I presented this slide, and I said that for all the tests that were performed with 75 degrees, the duration of the charge was the same. Actually, with the orange and yellow one, so at 800 kilogram per hour and 600 kilogram per hour, we have started recording things before we started the charge.
Okay.
So actually, that's why there is a difference. So actually, it's the charge lasted longer with 1,200 kg/h than with 800 and 600. Yes, that's it. And so that's why, because the slope is exactly the same, but just there is a delay here. I'm sorry, that's it's good that you pointed that. Okay, so with the internal charge, so there are 7 heaters inserted in tubes in the tank. The total heating power is 3 kilowatts for the 7 heaters, and the heaters are controlled. There are thermocouples in the PCM near the tubes in which the heaters are inserted, and if the temperature measured reaches a set point, the heater is stopped. And there is a hysteresis. So, for example, when we say the set point is 80 degrees, when the heater reaches 81 degrees, the heater stops. And when the temperature reaches 81 degrees, the heater stops. And so the temperature then decreases. And when it falls below 79 degrees, the heater starts again. So we did 2 tests in nominal condition, so without any forced movement of the heat transfer fluid. And we also did tests in which we turned on the pump of the external charge. So only the pump, not the external heater, but we forced the circulation of fluid in the tank. And I present you the comparison of the 2 tests. So in dashed lines, you have the sensors when there is no flow, and in plain lines, you have the sensors with flow. And here is the temperature of the PCM near the heater. So it's the temperature that controls the heater. And you have 7 curves corresponding to the 7 heaters as a function of time, and the total duration here is 9 hours. What we observe is that the temperature increases. There is the temperature plateau at 70 degrees. And at some point, the temperature stops increasing, and then the heating is stopped at some point. And just before heating is stopped, there are oscillations in the heater. So these oscillations are a sign that the set point temperature is reached. So the heater stops, starts again, stops, starts again, stops. And eventually it stops. And the heating stops after 15,000 seconds in the case of no flow, which corresponds to 12.5 kilowatt-hour transfer. And if there is flow, the heating stopped after 20,000 seconds. So the energy transferred was much higher than previously, which tends to show that it's more efficient to have flow of fluid in the tank during the heating. And here is a graph presenting the temperature around the tubes that are not heated. So the tubes that are further from the heating elements. And there are 3 curves for each test. In red, the maximum temperature. In blue, the minimum temperature. In green, the average temperature of all PCM temperature measured, but further away from the heating tubes. And what we can see is that when there is flow, the minimum temperature achieved around the tubes that are further away from the heating tubes is above 70 degrees. So it means that PCM has melted everywhere, not near the shed, but everywhere in the tube bundle. While if there is no flow, the minimum temperature here is 65 degrees. I'm too late. Okay, so it means that some in the efficiency of the charge is much lower if you have no flow. I have to speed up a little bit. Well, here it's just a localization of sensors, but I'm almost finished because now I would like to present some tests that were performed in ComBioTES discharge, so with the mixing valve. So the mixing valve looks like that. There are two inlets, cold water, hot water, and one outlet, which is mixed water, and the temperature of this outlet should be constant. So this is in French, but it's what was supposed to be done. It's in the specs of these components, and we did some tests modifying the set point of the valve. You can go from minimum to maximum. It's from 0 to 7, and we did some tests changing the set point of the valve. And actually, you have here two tests. In blue, it's the hot temperature. In orange, it's the cold temperature, so hot and cold inlet. And in gray, you have the mixed outlet. And it's not constant at all. There is no possibility to control the mixing temperature using this valve. That's a conclusion. So I arrived to the conclusion of the presentation. Here is a synthesis. We did hydrological charges and discharge in clean conditions. Some elements are presented here. Regarding the external charge, which showed that it's the energy charge is higher if the flow rate of the heat transfer fluid is higher and if the set point is higher. For the internal charge, we show that if there is a forced flow of heat transfer fluid during the charge, the temperature homogenization is better between the two bundles, and the energy that is possible to charge is higher. And in discharge, in the ComBioTES mode, we showed that the operation of the mixing valve is not satisfactory. And here are some next steps, because I presented you only some points, and you can see that there are some things that we still don't understand. So we need to continue working with this prototype to better characterize it and understand its behavior. And I'm ready if you have other questions.
So what do you think is best for, I think, either the spatial heating or for this hot water for showers and so on? Is one, would you prefer to use this PCM for one or the other, or it doesn't really matter? Well,
for space heating or for shower?
Or shower.
I think both. I'm not sure that's well, at the moment. I would not use it to take a shower because it would get burned.
Okay.
Yeah. But this can be modified. You just probably chose the wrong component. But otherwise, normally the performance of the system should allow to use it either for space heating, but also for domestic hot water.
Any questions maybe from the audience online before we go to the next session? If you have any immediate questions.
In the chat are not all already answered.
Okay. Okay. Yeah, you can also write down your questions directly in the chat, and Arno will take care of them. Then we can go to session number 2, Anish.
C'est toujours trop long. Tu peux présenter les résultats.
Okay, so I'm Anish Chandra from DTU, and this session I will be talking about the real world performance of the prototype. I'll talk about how we integrated it in our test facility and the development of an intelligent energy management system. So this is the demo site at DTU. It's called Flex House. It's a 3-story building with 2 bedrooms, and it's a smart building in the sense that we are able to control all the hot water radiators in all the 3 floors, and it is equipped with temperature sensors in all the living rooms. So we are able to communicate and control the building. There is a schematic showing so we have the heat distribution system, which from the storage we supply heat to the building through these hydronic radiators, and the building is also equipped with local PV. So the idea behind this setup is basically to use renewable electricity, preferably local PV, to convert it into thermal energy, and then use the thermal storage capability of our prototype to deliver and cater to different heating needs. In this test setup, we focus mainly on space heating for the building. And the idea is to demonstrate saving of the device operate in. Okay, this is a schematic of how the prototype is actually connected to the building heating system. On the left side of the left loop is the external charging loop where we can charge the PCM, and then on the right, the secondary loop is the discharging loop, which supplies heat to the building. Okay, so this is in our heat distribution and to these bays, which then deliver heat to the building. The prototype is situated in this heat distribution substation, which is just adjacent to the building, Flex House 3. So this shows the different components of the device that we have received. The PCM tank with level sensors at the top, the POD device that contains low-level controller, high-level controller, and data management and the energy management system, the various components such as the external heater, the flow meter, the pump, the safety control, which is hardwired safety, and the different valves. So all the sensors and instrumentation is located in the electrical cabinet, which are then connected to this POD device, which has all the intelligence, which receives all the sensors, processes the data, and then controls the operation of the prototype. So this POD device consists of, it's an edge computing system. It comprises of a Linux PC that collects all the data and stores all the data, and then hosts visualization tools such as Grafana dashboard to view the historical operation of the system. And we run all the different controllers, the low-level PLC controller and the high-level EMS controller on this system. And it's also equipped with a 4G router with VPN so that there is remote access. We are able to remotely communicate with the prototype, and also it enables data sharing across different demo sites. This shows the integration of this prototype within the electrical network that we have at our research facility. Basically, it has two electrical power sources. We can directly import electricity from the grid or from the local PV that is produced for heating the storage tank. So the local PV is this set of PV panels which amount to around 18 kilowatt peak at nominal conditions. This is just located across the substation. So we try to prioritize electricity consumption from the local PV if possible, and then if not, import from the grid. So the data flow is basically all the sensors, measurements, devices, all the digital inputs are analog inputs. They are delivered or through Modbus protocol communicated to the PLC controller, which is on the Linux PC. And then these digital inputs and analog inputs are processed by the PLC. And then through an OPC UA interface, they are sent to the EMS, which then is able to process and process the data and send some commands. And all this data or the commands through a router, we are able to share it to different sources externally. So there are a lot of inputs around 22 temperature sensors, 5 liquid sensors, water sensors, flow measurements. All these digital inputs are processed by the PLC controller, and then we have the possibility to execute commands to the different components, switching on the external heaters, the internal heaters, opening, closing valves, and switching on off the pumps. So this is all handled by the low-level PLC controller. And in the controller, we implemented a state machine which allows us at any time to be in one operation mode. And these operation modes are predefined, and there are safety conditions that do not allow the different modes to be operated out of those safety constraints. So the operational modes are basically a manual mode, which allows the operator to directly control the operation of the device, and an offline mode, which is meant to operate independently when there is no external communication or input, and an EMS mode, which is energy management system mode, where we are able to retrieve signals from external inputs and communicate and operate the device. The low-level controller, while processing the data, also we have developed a human-machine interface, which allows us to visualize the real-time status of the different sensors and components in our setup. So we can see the temperatures in the 3 paths, the temperatures in the internal heaters, the temperatures in the flow rates, the pump status, the external heater status, the valve status, etc. So it allows us to visualize the real-time status of our system while operating. So this shows the manual mode interface. which is a web page, and through which we can basically control all the components, the valves, the pumps, the heaters in manual mode. So we are able to characterize or estimate the state of charge using two different sources. One is the 15 temperature sensors that are located in the 3 parts, which allows us to estimate the temperatures, the state of charge based on temperature, while the other source are the 5 liquid level sensors that give us an estimate about the height of the liquid level. And then from it, we are able to estimate the state of charge using the liquid level. Of course, because there are only 5 liquid level sensors, which means that we are able to estimate the state of charge only in steps of 20%. And this chart shows the evolution of state of charge, like during a charge cycle and a discharge cycle. Um, yeah. Um, so we have performed some characterization tests initially in manual mode to understand the behavior of the system in real conditions when it is connected to the building, so that we can develop rule-based control and an intelligent control. This just shows one charge cycle at a constant flow rate of 1000 liters per hour. When we charge it from when the average PCM temperature is at 60 to 80 degrees, so we consider this zero charge and fully charged. We can clearly see that the solid PCM following gradually increasing temperature in the sensible mode and a clear temperature plateau. The 3 passes, we observe that the first pass melts much quicker, while the second and third pass, they melt later. And then again, the fully melted liquid PCM in sensible mode. This is one of the discharge tests that we conducted, where we discharge it directly to the building at a constant flow rate of 600 liters. And we observe that the outlet temperature is more or less steady at 60 degrees. And then we see the power delivered initially for around 15 minutes. The power delivery is about 20-25 kilowatt, and then it stabilizes and we achieve some stable power delivery about 5 kilowatts. The overall discharge duration we observe to be around a half an hour to 40 minutes, because the nominal heat load of the building is around 9 to 10 kilowatts, whereas the storage capacity within this 60-degree and 80-degree temperature range is around 10-11 kilowatt hour. So approximately 1 hour, in 1 hour, we are able to fully discharge the storage. And here we see the temperature profile and the state of charge profile. So during this characterization tests, we observed that we are able to store thermal energy of about 12 kilowatt hour, and we are able to retrieve almost 11.7 kilowatt hour back while delivering heat to the building. So indicating the very high round trip efficiency of about 98% at different flow rates. So this indicates a very good efficient retrieval of energy from the storage. So now moving beyond the local low-level control in the manual mode, the PLC controller, through this open OPC UA communication protocol, we are able to exchange data and control signals to the EMS interface that allows remote control of the system. And once the data is obtained from the PLC controller, it is then processed and fed to different databases. We collect data every 60 seconds and we store it on this influx DB, which is a time series database. And all of this data is pushed locally from the PC to the database using a Telegraph server client. So this shows the the interface of the influx database. We can see we can basically access all the different data, the variables at different times. And then all this data is then visualized on a Grafana dashboard. The page looks something like this, where we visualize the position of the walls, the status of different components, and the operational mode of the system historically. And yeah, we can also visualize the flow rates, the power delivered, the power grid import, electrical import, and production and consumption. So all sorts of visualizations that are relevant, we are able to visualize. So in the PLC control, we have the second mode of operation, which is an offline mode, which allows us to operate the system when there is no external communication. For example, there is no server issues, or there is no network communication, then it is able to operate independently. So in this mode, what we basically do is we charge and discharge the device in a cyclic manner based on state of charge estimation, so that we are delivering heat constantly to the building. So we can see this very uniform charge discharge cycles. And so the PCM is basically very uniform, stable charge discharge cycles. And since this offline mode has no information about the temperatures in the building or any other kind of external information, it may sometimes not be able to supply enough heat to maintain the indoor temperature within the comfort bound. We define indoor comfort as temperature between 19 and 23. So this is one of the limitation of this mode, but also this is a backup mode in case communication fails. Now we come to the EMS mode, which allows us to communicate with external entities. So the EMS is able to take inputs not only from the storage tank, but also from the building, the room temperature signals, and then use this information to control both the charging of the storage tank and discharging to the building, so that indoor comfort is maintained. So in this mode, so in the EMS mode, first as a benchmark, we developed a rule-based control whose so the rule-based control is defined to operate in a cyclic charge discharge manner, but with the additional inputs of the indoor room temperatures, so that it is better able to manage indoor comfort. So we observe the same charge discharge cycles as in offline mode, but because it has information about the indoor temperatures, it is able to schedule it to maintain indoor comfort within the building. Next, we come to the intelligent EMS, which is our main contribution. Basically, this is the schematic of the EMS, which takes information regarding weather data. So we obtain temperature data, solar irradiation, and then we obtain information about the electricity prices. And this, along with the current system state of charge, the current comfort level in the building, informs the EMS to schedule, hopefully in a smart and intelligent way, the charging and discharging of the storage. So we retrieve dynamically the weather information hourly, the solar irradiation and outdoor air temperature from an open source weather API. And then we observe that this forecast correlates well with our local temperature measurement sensors. So they are reliable. So we use them to inform our solar PV model. We use a simple PV watts model to estimate the PV production from the solar panels. And we see that this simple model is sometimes overestimating, sometimes underestimating, sometimes it estimates well. But more importantly, the timing of the production coincides very well. So on the other hand, we obtain electricity price signals, the day ahead prices for tomorrow at every day, today at 1 o'clock. From October 1st, the Nord Pool prices have moved to 15-minute intervals. So our control strategy is every 15 minutes. And we use the PV production estimate and the day ahead prices to calculate this so-called cost of charging. Because we know that the external heater is rated at 3 kilowatt. When we charge, the charging electrical consumption is fixed at 3 kilowatt hour. And we assume that the PV production cost, the marginal cost is zero. So based on these two inputs, we are able to create a estimated cost of charging profile. And then we classify this cost of charging into high price periods and low price periods. Basically, when the prices are at a one standard deviation above the mean, we classify them as high price periods. And when they are one standard deviation below the mean, they are low price periods. And sometimes we observe that when there can also be price periods where it's negative. So now the idea behind the intelligent EMS is to schedule the charging and discharging while taking input of the cost of charging, considering the current state of charge and indoor comfort. So we see here that in normal, when the prices are normal, the charging and discharge cycles happen regularly as before, but charging is limited only up till 72 degrees. We don't fully charge to that. There are low price periods. We try to extend the charging. So we extend the charging up to 80 degrees. And when the price periods are high, we avoid charging until just so that the indoor temperatures do not fall below the indoor comfort boundary. So this shows the capability of this intelligent EMS to respond to dynamic electricity price signals, considering local PV production, and then adapt the charging and discharging of the prototype while keeping the indoor temperature within our predefined comfort limit. This shows the same schedule, but the grid import and export. Basically, we try to avoid importing electricity from the grid when the prices are high, and when the prices are low or when the cost is low, we try to import fully. That is fully charged. Yes, and we also try to maximize the utilization of local PV so that when there is PV production, we minimize export to the grid. So the developed EMS and the implementation show that we are able to achieve energy flexibility in terms of shifting the load and also reducing the peaks. Of course, the degree of flexibility depends a lot on the capacity of the storage, also on the capacity of the building, the sizing. Yes. So during the past 3 months of testing, we faced quite a lot of technical challenges. One is that sometime in the first week of October, there was a power outage in Denmark. And even at a research facility like DTU, all the systems.
No. So this house has a base load in conditions like we have now, a fall day with 15-20 degrees of 10 to 15 degrees, around 3 kilowatt continuously.
So it's, yeah, but that's.
Of course, also depending on,
The
yes.
outside temperature.
Yes, the outside temperature, of course. So the base load is actually rather high, and it could supply heat for the house.
If I can add just a few words about perhaps to explain
Yes.
situation.
Yes.
That initially in the project we were thinking about domestic hot water, and so that's why we have this kind of unbalance between the charging time and the discharging time. So that means like you have at home, you are charging for discharging the water tank in 30 minutes. And for the seating, and the second element that is that it was the first element, but it was not really consistent with the needs of an house. And the second one is we wanted to have the same prototype on all demo sites to make the comparison, even if it leads to some kind of not a good agreement between the demo site and the needs. So that's why for the next generation, if there's some next generation, we need to adapt this design and to change some elements. The technical not the requirement at the beginning were not the one of the C-slab house.
Flow rate. 2 days or 3 pump for the central heating. And it's 2,500 kroner you can buy a Grundfos pump that is can adapt according to the speed and so on. Everything works by itself.
So, yeah, in the chat.
Uh,
In the chat.
okay.
There.
Okay, so we have a question from the chat. Will the operation of the pilot continue after the project? And will the Grafana interface be public for others to observe? Regarding the first question, it is expected that the prototype which is at DTU and the prototype which is at CEA at 2 sites in Grenoble and Ines, that we will continue some characterization tests, further tests at these sites. But I believe this is not connected to the.
At CEA, nothing is connected to the outside. This is a basic rule of safety. This is something that could be changed perhaps, but it's really complicated.
Yes. And the Grafana interface is actually publicly available, and it will be shared by our communications team.
So hello everyone, and welcome back. It's 11:15, so we will continue this workshop with a presentation from work package 6. So we have Aziz, work package 6 leader, joining online. Aziz, I'll give you the floor to tell us more about what you are going to present.
Okay, thank you so much. So good morning or good afternoon, different places. Now I'm Aziz Rahman. I'm working for Technology Solutions Limited. We are sitting in Manchester, so we are a partner of ComBioTES project, and we are developing, we are leading work package 6, which is the techno-economic, environmental, and other different tools as a decision support system. So I'm going to share my screen, so the computer screen, so that we can see a little bit on the detail of this. I hope you see it.
Yes, we can see it.
Okay. So this presentations, what we are going to talk about, the different tools, will be in two parts. So I will be presenting techno-economic, like environmental, and the DSS one part, and then our colleague IEO, they will show us the financial and market analysis. There is another tool. So that these all our tools are seen as a kind of compact output of the TVA of the ComBioTES project, which could be used even after the project is finished for different components and different variables. So first I will talk about the life cycle levelized cost of storage and what we did life cycle analysis tools. Then we talked about the kind of knowledge base or database that has been used by decision support systems, and then we see a tool for the sustainability analysis. So all these things is a combinations, and we put it together in a decision support tool. So for the levelized cost of storage, we use this formula. So this is used to calculate the cost and compare the price. So we run the levelized cost of storage, and then we calculate the average discharge maximum discharge and minimum discharge for these three scenarios, and the calculated value is around in between 0.175 to 180. So we also ran some more Monte Carlo simulations to understand the uncertainty and to check the variability in prices. So as you see that the Gaussian distributions and between these values are 0.17 to 0.18 euro per kilowatt hour. So this is we checked also with the literature value. This is within the range for similar kind of solutions or storage capacity. Then we performed, so for this life cycle levelized cost of storage, we have developed the tools, and it is integrated in the decision support system, so anyone can change different input parameters and run the simulations. Then we perform life cycle analysis. So we use SimoPro software, and this is maintaining the ISO guidelines, and we use the CP midpoint H method. So the functional unit, we considered 1 kilo energy delivered by the storage. So for the life cycle analysis, we basically consider cradle to grave system. So that means it should be construction phase, use phase, and end of life. Basically these three phases we compared and we calculated. So this is a high level ideas, those like who are not too much familiar with the life cycle analysis. So there are like basically 4 steps. So we do the scope and definitions, then we do a intensive life cycle inventory analysis, then we analyze the impact. So using the SimoPro software, basically we can analyze 18 types of midpoint impact, and then we interpret the results. So one of the results is like this. The left hand side you see the network model. So it shows that okay, what are the percentage? You can see here the percentage of CO2 or CO greenhouse gas emissions here, and in different numbers. So you see that the use phase is the most important phase, that is 77%. Also we can here in the lower level, we can see the different components, constructions, metalworking average for chromium steels and other steel products. So different components of the main components of the storage system, and what is the percentage of and also here you see the numbers. So numbers are so small, but in kg, but you see the percentage, and you can see which one is contributing more on this. So here in this side, this also the tool also produce in different 18 midpoints impact categories. So it's health, ecosystem, environment, and these 3 color shows these different phases, which one is contribute towards. So this is also giving like extensive impact on the ecology and the environment. So this life cycle analysis, we have already developed a tool for the ComBioTES system that can show us these results, and it is implemented in a decision support tool, this platform. Then also we compared with another PCM, and then this and the results for this 18 midpoints is also showed here. So idea was to compare with another market ready PCM, and most of the time you see that RD70 AC is a bit better than the other one. So it's not easy to get all the relevant data for the PCM, because a lot of PCM data are like confidential, so they do not we do not get always the details, so that we could perform a lot of LC with different PCMs, but still we could manage some. Then this LC is also included in a decision support system that we develop in under the ComBioTES project. So there is also a database and knowledge base where we have 3 types of modules: demand analysis modules, then we have thermal energy storage modules, and system testing modules. So here we put all the results of the ComBioTES, and also here we put examples of the ComBioTES, and also we got some literature data like PCM properties from literatures and put it here. So, and also there are some other EU projects that we develop further on materials and heat storage. So we also included those data from those databases here. And this is some of the screenshots that we developed for the PCM. So we can see here some data, here some data. So this data can be used for in the DSS. So we show another module that uses some of the data that is required. So there are some more on this, like this is electricity pricing, storage system parameters, latent storage. So all those things are newly developed under this project. There are some more on the PCM properties. So we collected a lot of PCM properties from different literature. So these are already here. So one can, it is like of cumulative. And also we put like heat transfer fluid properties. This is also a collection of different databases, and we put it here that are relevant. So this combining all those like databases, life cycle analysis, levelized cost of energy, and also the sustainability model called multi-cat analysis, we developed a decision support tool. It is a web-based tool. So if and it contains, there is a heating demand calculator, there is a preset demand model database, then economic computation model. This is basically here we are calculating the levelized cost of storage, then here we are calculating the life cycle impact, LCA. So this DSS, so this is a like the portal that we have developed already. So there those things are already included. So one can sign in and then get our permission to use the DSS. Then this DSS, this is some of the screenshots that we have for the demand calculator, some parameters. We see also that these decision support tools are here, like economic analysis. So all those things that the user can define their value and get the output. So the idea of these tools are like that we are not developing the parameters related to only for this ComBioTES specific storage system. So even if someone wants to design a new one with new capacity or something else, then one can change the input parameter and can also calculate their own like TS prototypes results. So varying different storage capacity or charging cycles, and so on. So this is like a kind of generalized tool so that one can change the different parameters and can run the system. Yes, and then this is another one that we do, the multi-criteria analysis. Basically, we have been developed this one and integrated in the DSS. So this multi-criteria analysis, this is used for ranking of different solutions. So it could be like different TS thermal energy storage system with different properties, different economic values of the size. So, but one is always like a kind of trade-off to see that whether economic criteria is much better than the environmental one or not, and then at the end combining like social, technical, or environment or economic criteria, one can define which is the best combinations. So this multi-criteria analysis has been used by different domains. So we are using here to analyze the sustainability of a kind of thermal energy storage. So this, so what we did, we developed the tool in a way that it can develop different hierarchy. So the different here is like 3 level of hierarchy. So sustainable combat is our goal, and then we consider technical parameters, economic parameters, environmental parameters, and social parameters. So these are the criteria that we selected for this exercise in the ComBioTES. And we define 3 options: model 1, model 2, and model 3, with different capacity and different other parameters. So basically what we say, the goal, mind criteria, and the alternative. So we using those criteria, we define or rank the alternatives so that we choose which one we would like to go for, or what are the trade-offs we can consider. Then if we see that these are model 3 models, so all this criteria, we calculated the values and using our tools that has been developed, and some of the tools values maybe we took from the literature, and these tools has been used in the ranking of alternatives. So what it does, basically, the user can give weightage of different criteria. So importance, maybe the scientists, maybe most of the time they are more concentrating on the technical efficiency. So so they can put importance on the technical things, but maybe for the people, like if the user, they are more concerned on the price or the cost, then maybe they give more importance here. So one can, in this software, one can define the importance, and then according to the importance, we run some overlay method like weighted linear combinations or TOPSIS. There are a lot of combination methods. So we implemented 2 of them, and then based on this criteria value, it ranks all those things. So in our software, we can also see that in terms of like technical criteria, which one performs better. Here we see that model 3 performs better, but in terms of maybe economic criteria, model 1 performs better. So one can see that is not one option is not always the best for all criteria. So then sustainability means that it should be like a kind of balanced between all the prominent criteria. This we see in here. Yeah. And then the software is, then we combine this and we see that, okay, model 1 outperform the other 2. And we see this is the dashboard that we have been developing ComBioTES. So again, this tool is very generalized. So one can change the options and different values, and can use different scenario value and own weighting and normalization. So this could be used by the user or the beneficiaries, also for the technicians, whoever would like to select the best one. Yeah, I think this is the first part that we talked about the DSS tools and life cycle cost analysis, levelized cost of energy. Now, our colleague from IO, they will present the financial and market analysis. This is an excellent tool that they have developed under the ComBioTES. So I'm sharing. I stop my sharing, and I give the floor, or should, and then we can discuss if there is any potential questions. Okay.
Thank you, Aziz.
Okay, so I should take the floor right now, or we're waiting for questions?
I think, Konrad, you can go ahead with your presentation, and then we can take the questions at the end.
Okay, great. So let's start it. Um, okay, so I'm Konrad Wiśniewski from Institute of Renewable Energy in Poland, and I would like to show you a little tool that we create for ComBioTES project. From our part, we are responsible for, let's say, prosumers point of view and the needs. So we focused on that, and that led us mostly to the application connected to the hot water distribution and acquiring. And we prepare this tool to probably for the installers, maybe just for the interested prosumers that would like to install heat storage, especially phase change heat storage in their facility. And I would just show you this web tool that we created. Our idea is to, let's say, in a most possible comprehensive way, show what they need to decide, for example, what size of storage they will want to need. This tool at the beginning, right now you have see the energy statistics, so it is basically this area is basically telling what kind of system we are looking for. All of this parameter can be changed below. For example, you can change the power, solar power installation, and calculate it. And of course, you can see the change of how many photovoltaics energy from photovoltaics are left in the system, and then it of course can be used to create hot water from our installation, for example, from music. So of course we include the comparison between water storage and before you have a really detailed presentation of how the music works. But right now we needed to combine it to very simple parameters. As you can see, there is a storage size here, and of course the losses that are estimated per hour for our storage. In advanced settings, you can change the unit capacity, for example, and of course some roundings, because for numerical reasons there needs to be some roundings in calculations to get it fast. We also so this first part is for storage. The second part is the definition of the system, and this definition of the system can also be we can view it in the charts below. So this is our hourly average with 1 day PV production, heat demand, and electrical energy demand. So this is the starting point, and of course we need to get the energy prices from the market. There are two of them, because one of them is sell prices that we can sell energy to the grid, and another part is the price at which we buy energy, because this one will contain the distribution cost, so it will be more expensive. In this tool, you can check each year, and you can see that the prices are changing, or you can generate the most actual price profile. And also, if the user want to, one can use their own data that can be limited, for example, for their location. Right now, everything is, let's say, pre-installed in the system, but anyone can give to the app 1 year of PV production heat demand. There is also one information that all of this application is based on 1 year analysis, because it's of course easier to make some assumption about the economics from the 1 year and further. So this is our setup, and after that you can always click the optimization button. It will take a few seconds, but I will go at the end of the application. As you can see, there is some comparison. You have thing like storage utilization. This is kind of important parameter, important with the comparison, because at some point you can see that that storage utilization, when you have the water, for example, water storage, it will be full. And if you change the phase change material, it will be less. It's because for example, size of the storages can be different. So someone can say, okay, we can make it a little bit less and try to get the right sizing. And this is important for installers because they know that, and for prosumers because they know that they can acquire small sizes storages. You have also here the summary, the losses in the system as it was set, and the cost of the system. Right now it is in Polish zloty, so you need to divide it more or less by 4 to get the cost of heat that we obtain from the grid. And you can also see how much of the hot water we can achieve from photovoltaics in this household. And it should, so basically, if someone have no idea, I can run this app as an pre-calculated setups. If someone have some knowledge about the system, can add their own files and see what will change during the analysis. These apps have also some manual, I hope quite a comprehensive manual, how to use it and how to read the results. There are also some information about some limitations of these calculations. If someone is, let's say, more advanced, they can also look at this. And we hope that this tool can be useful for sizing and for someone who will try to who are considering the storage, the heat storage in their households. And I think that's I cover more or less more of the features of the applications. So thank you. Thank you for your attention, since that's all from me.
Thank you very much, Konrad. I think there is already a question in the chat. I can read it out. Does take into account the non-constant power output of the PCM test?
This is already at this point, no. At this point, no. It is we simplify it. It will just prolong the calculations, but so we left it at this point. But this is something that we can include, of course. Even let's say for more. We also think that if someone will wait a little, like more than 30 seconds for the outputs, it will be problematic for this app to be used by installers. But of course, we can extend it to this point, and let's say a little bit extended the time of calculations, and it can be done.
Well, have you tried it on the pilot plant here at DTU or the pilot plant at CEA? I haven't tried to calculate sort of rough numbers for those.
Mm, can you repeat the question?
Have you tried to make the calculations for the pilot plant here at DTU or for the CA?
Right now, still we still, because the data from this facility is quite new. We didn't incorporate it, so we didn't have an exact comparison. But of course, yes, this should be done.
You have 2 more days to do it, was it?
Yeah, sure. I will try.
I hope your code is fast.
Any other questions from the online audience? No? Then thank you very much, Aziz and Conrad, for sharing the
Thank you.
results from work package 6. Now we are approaching the end of the workshop, and for the closing part of this workshop, we thought that would be both interesting and helpful to share some lessons that we have learned over the course of this project. So you will hear some lessons from work package 5 and work package 4. So I'm gonna give you the floor, Arno. Just give me 1 second to share my screen.
No problem. So, maybe as you may have understood, the project was not a straight line from the beginning to the end without a lot of trouble on the journey. So we try to summarize some of the elements that have been faced, and most of them are common sense, but sometimes it's a good thing to remind some common sense. Just the music prototype, basically what it is. It was a kind of common work between different partners, with 2 partners being involved in the manufacturing, namely Delaunay, the boiler maker, and CA. DTU, which is working on the EMS PLC, and the demo site's partner. So it depends, it could be CA, it could be DTU, it could be IEO. So that means that to be successful, we need to be successful in connecting all these elements. Something. Oh, yes. So, and just to continue, basically, one partner, Delaunay and CA, was provided a PCM tank with some key components, some valves, some sensors, some regulation and safety directly included in it. So it was a very good idea on the paper, and he has a very good drawbacks when after experience, some integrated safety features, some electrical connection made by a subcontractor of CA, and the tank was filled by CA also, and then it will be delivered to partners to connect on its own utilities, electricity, compressed air. So that means that we have interfaces. We have to make some hydraulic connections. So you have some interfaces, and you have to be sure that everything is working properly. Then you have to install the EMS, and you have some interfaces. The data acquisition, and you have some interfaces, and a lot of stuff like that. So if we come back to this scheme, so that means that in fact we have interfaces everywhere. And I think that all partners individually has a lot of experience at doing its own job in its lab, in its company, in its factory, without interfaces and with minimum interfaces. But if we continue, for example, just for EMS, so that means that we have to know for the guy developing the EMS, you have some question about the connection of an so-called autonomous system with you have to connect this so-called autonomous system in an existing system with a not so known system because it was not built at the time the VMS is developed. You have to prepare everything without data and without final element. A lot of information has changed during this process, and you have some repetitive delay. And so you have to be finely prepared and finally ready at the right time. Looking for the manufacturing, you have to, it was just a kind of internal receipt, but all the budget was given to not to a single partner because it is not how European projects are built. So that means that the budget is between CA, between Delaunay, between other partners to build a single object. It's not so easy. So that means you have to, some partners are making the specific, the technical specification, but it is not the same partner that will make the others. This is the first problem. Then you have some coactivity between the manufacturing and the instrumentation. It was perhaps the easiest part of the process because we have already done such elements. Then you have a lot of legal regulation aspects because basically this is not our expertise. You have a lot of element about legal aspects because we are one partner is manufacturing something that is delivered to another partner, that is filled with another partner, and finally given to a third partner with some modification of a fourth partner. So that means, legally speaking, normally we should have contract between everyone. If we want, because if something happens, and finally, all these elements, oh, maybe that's a little, this is not a problem. All these elements should be included on the demo sites. So I just, the situation was more or less the same on all demo sites, but I considered the Polish demonstration, which is the most complicated one from far. Just because the first element, the demo site is really far from any partner. It was near the border of the Poland. It was really far from any partner. It is a real demo with a real family inside, and they want to take some shower. And cold shower and not cold shower, and they want to not have some sickness issue due to the quality of water inside the shower. And basically, this is not a lab, so that means the electricity, the maximum weight, the presence or not of compressed air, nitrogen is not the same as in lab. You have to. The ability of some data for the preparation is quite different between a lab and a real house. I'm not sure that you exactly know what is the maximum weight acceptable, but at your house, I'm quite sure you don't. Basically, you have to adapt because the demo site owner will not build a new garage or something to install the prototype. And you have a lot of regulation and a lot of legal aspect. You need some owner fee or a contract. You have all the regulation linked with the domestic hot water, the insurance, the responsibility, who is responsible for what in case of anything, the permitting, who is doing the on-site work, what kind of contract do we need between Delaunay, CA, IO, DTU, what should be the commissioning. We never think about the commissioning, but these people will normally will receive a prototype as this prototype should be decommissioned. So that means that considering all these elements, it's really complicated. And so as a coordinator, if I would like if I have to give very simple reflection, when you build a proposal and during the project, you have to stay optimistic. This is really important because finally Anish presents really interesting results, but you have to consider that maybe DTU was expecting this prototype for more than 1 year. And we succeed in the transportation, we succeed in the installation and in the exploitation in the last 2 months of the project. So you have to be optimistic. And you have to be agile in a way to manage every deviation, and you will have a lot of deviation. You have to be, and this is something really important and something that is never made, you have to be honest about the TREV, the technology readiness. Because in general, in the lab, when you have tested one component for 2 hours in perfect condition, you say, okay, this component basically is almost industrial, but it is not the case. It's just a lab component. And now the European Code are asking for TUL7 because we have said since years and years, many years, that we are at TUL6, but we don't. So we have a big problem, a big issue. You have to be realistic when considering and when writing the proposal about the demonstration, because everyone said, okay, I will have 4 sites of demonstration plus 4 sites of replication. But in fact, once you start the project, you have to consider 4 sites of demonstration and 4 sites of replication, and it's quite complicated. Something that is really, really important for me is that never install something in real house, never. Because if you want to install something in a factory, in an industry, these guys have the habit to see industrial products. This is not the case for a real house. And real people don't want to, real people have in mind what they can buy at Conforama, in a classic store. So a prototype with real people is really, really complicated. What can I say? Something that is really complicated, and even at the end of the project, maybe we didn't succeed. And now if we have to do it again, I'm not sure that it will be better, but we will fail a lot of elements. This is define all interfaces. But it's easy to write this sentence. It's horrible to really imagine what are the implications. But you have to define all interfaces and with the related budget. Who is doing what with what, which budget, when? It's really, really important. You have to start everything on a demo site long before the fake planning that has been submitted to European Commission, because basically, if you start at the normal date, you will fail. You have to start from the beginning to be prepared when you have to really start the demonstration. For each demo, you have to be sure that you have a single person or a single team, a qualified team that will lead the demo, that will able to know that to do that we need this point, this point, this point, and this point. If not, you will fail the demo. And even with this kind of precautions, I just want that the Murphy's law applies, and it may be complicated, but just remember, session 1 and session 2, at the end, it may work. This is important. Stay optimistic. So from just coordination and administration inside, not about technical aspect, but really coordination, the main question, and I'm not sure I was the best person to really do that, is how do you maintain motivation, involvement of team from different group, different country with different constraints when you have a kind of dotted line project. So when you don't know when you don't know what will happen when, so it's really complicated because with all the delays, you say to a partner that okay, your team should be prepared at this date, and 6 months later you say okay, this is now in fact, and 6 months later you say the same, but it is not possible to plan a team like that. But it's complicated. Just to remind, for example, in the ComBioTES project, the project started in 2019, and after 1 month, he has been suspended. He has been paused for 1 year and a half. So for most of the partners, the project was dead. And so that means they have to remotivate and to reallocate people to this project. And I would like to thank everyone, because that means that everyone did this really complicated task. Finally, after regarding what has been proposed, the initial concepts were it is written inconsistent, but sometimes I will not like to use this term, but the project was physically challenging in a lot for a lot of elements and not so relevant. So that means that you have, after one point here, you have to redefine what you want. The PCM provider that is included in the project, and it was a really good idea. But finally, we said to this guy that okay, nothing that you are providing is okay for us. So it was quite complicated also. The main industrial partner was no more interested in the project and has to be rejected. So that means we have to find a successor, and we have to find someone to manufacture the prototype, to install the prototype, and perhaps even to do the maintenance. So that means that we have to make two major amendments and to redefine the budget, but more important, to redefine the task and to redefine the interfaces that were not really initially really known. So we do what we can at this time. We have to redefine all the responsibility. The interfaces were clearly unclear, and at the end, it is maybe clearer, but it is not the best situation also. Something that has never been assessed during the proposal is in the complexity with the European regulation, the non-European regulation, the transport, the contract, because in most of these kind of projects, there's no contract between partners. I asked a question to my legal service, and perhaps it was the worst idea I had, because they said that without contract, in fact, if something happened, we are all responsible. So I spent almost 2 years to make some contract between CA and different partners, and perhaps I will succeed, but 2 years. And just I would like to say the last sentence written is that maybe the most used phrase, the most used sentence I said to the partners is, okay, it will be available in 3 months. Just believe me. For more than 2 years. So it's difficult to remain really to be fully to convince people. So just to finish, something I really want to say that this is really important for me is that it is really important to have a good pair for administrative and coordination aspect. Just a few seconds.
De portvagten sirenealarm er en prøve. This is the gate. The siren alarm is the test. Slut.
Because I'm doing the coordination, the technical coordination, but in fact, I'm not doing the administrative coordination. And if I have to do both, maybe I will not be here today to speak to you. And I will terminate the project by myself. So thanks, Christina, now, and thanks, Eleanor Eleonora, who was coordinating the project with me before, because that means that I can focus on some technical or more technical aspect, but I do not have to focus anything about all the UPM portal and UPM protocol aspect. And it's not possible to do both. For me, it's not possible. It is really important to have a good feeling and a good relation with your colleague. And I'm speaking mainly about the CA team, because a lot of people have been involved in this project. And I would like to thank Benedict, who is with me here today. Pierre Adrien, who make all the instrumentation of the music prototype for DTU, for Grenoble, and for the Versatile 1 and 2. Jérôme, Fabrice, Guillaume, who give some expert advice and make the simulation. Awa, who is doing all the data reduction of the Versatile. So that means a lot of people are involved and they are not known in this project at the moment. It is really important because I know that my chief is hearing. It is important to have a good hierarchy. And to we spent, it was quite complicated for the hierarchy also, because we have a lot of delays. So that means that they have to plan something internally that was never expected. I would like to thank my chief, Raphael, Stéphane, Nadia, and Pierre now. And Raphael, really, I would like to thank you just because you accept to give extra budget for the building of the new test section. And without this test section, there's no Versatile. And it's important to have a good consortium and good partners, and to have people that are able to lead their own task. So thank you to She and DTU team, to Antoine and Ines team, to Aziz and TVS team, and to Gregor and IO team. And maybe it's if now at the end of the project was something to show, if we succeed something, we can say that this is mainly your work. And just to finish, I would like to consider my initial slides about the objectives of the project. About the development of two thermal storages, one called Music, latent PCM storage called Music, and one called the Versatile, doing heating and cooling. We have to make deeper analysis, but we can consider that it's okay. They have been developed, they have been manufactured. The global performances are not so far from the expected performances. So, about the development of a new bio-based PCM for heating and tap water, we did what we can, and it was not a success, but we had a backup, and frankly speaking, the development of a new material should be a dedicated project. So it was not the case in the development of the EMS. Maybe just for those who assist the workshop, the session 2 of led by Anish just proved the efficiency of VMS developed. So, and the demonstration at TRL 6, just keep in mind that a few minutes ago, I said that never overestimate the TRL. For me, we are not at TRL 6, but for the European Commission, we will say that we are at TRL 6, and so we are participating to this spec value of TRL. And basically about the demonstration, in Grenoble, it has been made, but it was the easiest part, because this is not demonstration, this is characterization. In Beijing, it is ongoing, and just for me, it was one of the most complicated, because I have to manage all the legal aspects. At DTU, it's working, and the session 2 is confirming it. At IO, unfortunately, we terminated the demonstration maybe in May 2025, just because we were so close to the success, but we have to admit that what is feasible at DTU and what is feasible at INES in 2 or 3 months is not acceptable for a real demonstration. So it was preferable to terminate this. And at INES, it will start tomorrow, but it will be made before the official date, before the end of 2025. So it's not my conclusion is from just the objective is not so bad, and most of them can be considered as okay. And so Shim from DTU will give you some reflection and insight about the work package 4 devoted to EMS.
Thank you, Arnaud, and thank you everyone for following the ComBioTES activity. Some of you followed the activity over the last 6 years, and some of you started to follow us since the morning. I really appreciate that you find this interesting. Myself is a senior researcher working at the Technical University of Denmark over the last almost 20 years. To me, this is a really nice project. Even though there are a lot of challenges, rarely we see projects that include, I'll call it the scientific discovery and engineering implementation. Because normally when we, focus on scientific discovery, then we put it clearer that, yeah, in theory it works, then leave it to someone who can make it work in the real world. And in this case, DTU and the CEA, and together with our partners, have done our best to make the PCM solution at least functioning in DTU's lab, and we have learned a lot. I try to summarize the learnings from DTU from 3 perspectives, because in this project, DTU has worked on several different tasks. So one of the tasks is called development and integration. That means we have to co-develop the solution, the ComBioTES solution together with CA in order to make the system function. And we also have to integrate the developed solution into not just our test bed, but also potential test beds that are available all over the world. So as Arnaud mentioned, there are a lot of interfaces. And again, we are very happy that the best labs, I think in Europe, CA's lab and the DTU's lab, can work together and get this done within a relatively short period. A lot of the information we didn't display today actually shows how complicated it is when we're talking about communication interface, electrical interface, thermal interfaces. The reason we managed to reach what we have reached today is because we have spent enormous effort on understanding the interface, communicating between the teams. And I'm so happy that even at the beginning, we were able to, I call it, speak the same language, which is very important. Because normally the scientists cannot talk to the engineers since we live in 2 different domains. But we managed. And the second learning is regarding testing and validation. It's kind of like a follow-up of the first learning element. But regarding the testing and the validation, we also have some special concerns and learnings. I have to say that I really appreciate that DTU is in this consortium and having Arnaud and the other partners, showing all the positive attitude since the beginning. Because from the testing and demonstration perspective, it's very true that the plan has been postponed again and again and again. And in the end, we didn't receive the unit on time. But last but not least, we managed to test and demonstrate an integrated solution, which is amazing. This is, I would say, is mainly because even though we do not have a realistic testing plan, but we managed to develop, I'll call it a contingency plan. So we sort of know what to do if things does not go as we planned. And for me, this is extremely important when we do research and when we do project coordination, as I know already mentioned. I would say that even though ideally we want to be successful all the time. But nothing is perfect. Basically, it's extremely challenging for us to know what is the best way to do something. But we always can learn from failures. And in this project, because we experience a lot of challenges regarding planning, replanning, we actually managed to deliver some realistic planning and carried out this testing, even though it's done in the last phase of the project, but we managed. So I think this is a very nice, you can say, learning from DTU perspective. And last but not least, I would like to talk about the EMS, which is the core deliverable from DTU. 6 years ago or 7 years ago, when we wrote the proposal together, we thought we could deliver, I would say, a rather intelligent EMS solution that it can give the best decision making, taking into account the amount of data we could measure and the amount of, you can say, auxiliary information we could get from global resources. And today I have to say, to a certain degree, yes, we have demonstrated certain level of intelligence. For example, the forecast that my colleague Anisha showed, some of the forecast is based on, you can say, machine learning algorithms. It is quite advanced. And also the algorithm developed by DTU have been demonstrated in simulation environment, which involves genetic algorithm for decision making. But realistically speaking, everyone knows that AI is trying to dominate the energy management system domain, particularly regarding the household level. Google has the Nest solution, Tesla has Powerwall with intelligent energy management, and the Siemens has home energy management solutions. So I would say that, is it still realistic for a single lab to develop some intelligent energy management solutions and let it compete with today's commercialized solutions driven by very powerful AI? This is something I don't know. But if you have a chance to do it again or continue the collaboration, I would say that the DTU is very willing to collaborate with those who are working on the cutting edge AI technologies and those who are able to get, you can say, testing and demonstration over 1 million of households rather than 1 or 2, 3 households. So I think this is very important. Well, last but not least, I really like to thank the team from DTU who managed to make this come true over the last 6 years. Thank you.
Thank you very much, Eleonora, for the kind words. Are there any questions from the audience? Anything that you would like to share or to maybe ask about our experience with this project? Anything in the room? Yeah, exactly.
Wrong morning.
One word on your first slide, that experiments are often delayed. I would say always.
Yes, you're right. And one of the main problems is that you cannot say the truth when building a planning and asking for money. And in France, we have all the nuclear power plants. And just if people said, okay, in fact, in 25 years, perhaps it will be made. No one will give money. So you said in 10 years, you will see the power plant. But this is a real issue that you cannot say the truth, because some people know that experimental work take a lot of time, that it's not acceptable to say that.
So just to wrap up, thank you very much to all participants for joining today for this workshop. Thank you very much to the whole consortium for the hard work that has been put in this project for like almost 6 years. Also, thank you very much to the presenters for sharing insights and for sharing the results. I think it has been a very interesting and challenging project and a very long and complex one, but we have learned quite a lot. And I think, as Arnaud said, there is still some work to be done at both CEA, Ines and Grenoble, and also at DTU. So we'll get more insights and more results, and there will be also many publications. We will also share the recordings of the workshop and the presentation in the coming weeks. So you will find them available on the ComBioTES website. We also delivered a first workshop back in February. So if you want to know more about the design of the prototypes, you can also watch the recordings or just read the presentations. So all of them will be available on the website, and you will also find the contact details of the presenters in case you have any additional questions that you want to ask. And with this, I think that the online part of the workshop is done, and people here on site can go for like a small visit to see how the music prototype is performing at the demo site. So we are very much looking forward to that. And thank you very much again for joining today.